In this video, we want to prove that square roots of distinct prime numbers are not rational multiples of each other. So let's take a look at an example to see exactly what it is that we mean by that. So if we have distinct prime numbers, let's say a 2 and a 3, and we take the square root of each one, if we can multiply the square root of 2 times m and end up with the square root of 3, then what we're saying is that this m must be an irrational number. In other words, there is no fraction with which you could multiply the square root of 2 and end up with the square root of 3. Spoken more generally, if p and q are distinct prime numbers and m is a real number such that this equation holds, square root of p times m is the square root of q, then m must be irrational. So we want to prove this by contradiction. We will first assume that m is a rational number and try to create a contradiction. So we can write m as being a fraction, since it's a rational number. We'll call that a over b, and a and b will just be integers. And we don't want that to be just any fraction, but a fraction in lowest terms. In other words, that it cannot be further reduced. We will definitely need that in the proof. We will also be needing the number theoretic definition of a prime number. So as we've already used p and q, let's say for an r. So a prime number here would be a number r that is a natural number that is not equal to 1, for which the following property holds. If r divides a product, let's call it CD, then r divides C, or r divides D. This definition we will also definitely be needing several times in the proof. So we'll begin by transforming our original equation simply by, at first, subbing in for m. So the square root of p times a over b gives us the square root of q. Now we can square both sides of the equation. And multiply through by b squared, which gives us pa squared equals q b squared. And here we can see that p divides qb squared. And we'll go off to the side here and do some calculations for that. So if p divides qb squared, then according to our definition here of a prime number, in fact, let's write that out over here. Prime number, that's just our definition here. Then that means p divides q, or p divides b squared. Can p divide q? Well, we know that p and q are distinct prime numbers. There's no way that one prime number can divide into a different prime number, so that cannot be the case. So this must be the case. P divides b squared. In other words, p divides b times b. And again, with our definition here of a prime number, we can see that p divides b, or here trivially, p divides b. We have no choice, it seems, so p divides b. And we'll write that out to the side here. P divides b. We want to remember that. And we can also use this opportunity to create a definition, an alternate definition for b. So b would just be some multiple of p, right, since p divides it. So we'll say p is equal to p v, let's say, where v is just some integer. And now we can return to our main line of thought and sub in for our b here. So that gives us q and then pv squared. We can multiply this out. We can cancel p's on each side of the equation. And we get a squared equals q p v squared. And now we can see that p divides a squared. And again, we can go off to the side and write if p divides a squared, then again with our definition of a prime number, that means p divides a, or again here trivially, p divides a. In other words, we have no choice. P divides a. So again, if we return to our main line of thought, we see that p divides a and p divides b. Which means that we can reduce a over b. But we said up here that the fraction a over b is in lowest terms. Therefore, it cannot be reduced. And here we see that it can be reduced. In other words, we have a contradiction. We have our desired contradiction. We had assumed m was a rational number. We now see that cannot be the case. M must be an irrational number, which is what we set out to prove. And that tells us that square roots of distinct prime numbers are not rational multiples of each other.